Okay, wow, we're recording, we're on camera. So welcome class. This isn't really a class. I'm going to be giving a lecture on GPU programming and architecture, kind of like, how a kernel, like all the, concepts around programming GPUs and kind of like how they map onto the hardware. Might be going into some stuff related to AI. I mean, Jensen Huang, bro. All right, anyways, yeah, so let's get into it. I didn't get his last name right. Okay. So yeah, GPUs from the ground up. Okay. So we're going to be talking about differences between CPUs and GPU programming models. I think it's kind of understood that, a lot of the guys here have taken, computer architecture classes and whatnot. So kind of.
Wait, can you go full screen?
Full screen? I think I've tried to go full screen on this, but I think there are some issues with that. I think this is the best I can do because I also want to be able to write on this, unfortunately. So that's the best I can do. Right. So anyways, so I guess I want to ask you guys first, what do you kind of like know about GPUs and CPUs and kind of like, just give me some like broad things, differences maybe.
Parallelism.
Parallelism, right?
Vectorized instructions.
Vectorized instructions. That's going to be a big thing coming up. But yeah, I mean, like, I think a lot of people tend to characterize GPUs as sort of kind of used more for parallel tasks, AI, ML, matmls, all of that jazz. I'd say something that also kind of like peeks out to me that I think that if you've like programmed with GPUs, you'll start to realize that CPUs, you have assembly, you have machine code, and that's kind of like the lowest level you have. GPUs, a lot of the kind of overhead is handled by compilers and drivers and runtimes and stuff like that. Abstractions that keep the programmer from having to delve too much into the GPU architecture, but we're going to be going into that today. So some useful terms for you to kind of know. Kernel kind of just means like, okay, the code that runs on the GPU. I think that like you guys mentioned, parallelism is kind of the GPU's biggest strength. So in reality, the code that we run, the stuff like functions, like calling functions and writing to files and stuff like that, not really something handled too much by the GPU itself or the kernel itself. Yeah. Saudi, you have your hand up?
Yes, Professor Khan. Why do they call it a kernel?
Same reason why they call operating system kernels kernels. It's because it's the interesting part. I wish they named these things better, but they don't.
Thank you.
Yeah. So we have stuff like threads, smallest of unit of execution on the GPU. You might be thinking of CPU threads, and NVIDIA certainly wants you to think of CPU threads, but they're not quite. A block. A block is sort of a group of these threads that it's like a shard of threads and data of like it's basically just a group of threads that runs on the same SM and shares, has something called shared memory, which is like a quick, fast, scratch pad memory that all the threads in that block can write to. A grid, and then a grid is kind of like, okay, how we launch these blocks of threads. And I could go into this a little bit more, but we'll kind of like, as we go along, we'll sort of come across these things. So who kind of familiar is like with CPU threading? Let's like first handle that. Any hands? Well, do you guys have to raise your hand every single time? Okay, cool. I guess you guys have to raise your hand every single time. I have no idea how to actually like. Okay, you guys know how CPU threading works, right?
Yes.
Yes. So you guys can just unmute yourself.
Sure.
So yeah, I mean, like you have kind of. I'm going to be using process and thread kind of interchangeably here, but this is sort of like, I suppose, a round robin esque example here where you have different threads and they sort of occupy an entire CPU core whenever they run, right? That's sort of the contract you have whenever you're a thread. You don't really know when you're kicked out due to, 100, nanoseconds or whatever, and, stuff like that, schedule of working. But in general is that whenever you run a CPU core, you have full unfederated access to all the architectural registers, all of memory. You kind of just do your own thing. And you don't have to deal with any of the performance hits when it comes to that whole. It's a round robin architecture, right? And as a result, different threads can sort of be completely different code. This one's like some PyTorch code here. This one is this weird program with a lot of while loops and conditionals, functions, etc. You sort of have this idea that a thread is a unit of execution in your CPU threading model, and whatever is in one thread doesn't really affect another thread. And whenever you context switch between these cores, you have program counter of that. You have all the registers, stack pointers, any data that might need to be backed up, stuff like that. So I kind of mentioned that, and you're going to see more about it later as to why that kind of example matters. So this is, we mentioned this earlier, something called a kernel. Kernel is the interesting part of GPU programming. This is the kernel. This looks like it's some sort of this looks like it's just normal C++. This sort of signifies to the CUDA compiler, okay, this is not just a normal function. This is a function that will be handled by the CUDA compiler itself. And you can't just go ahead and put like a hello world within this. It looks like it's normal C++, but it's not. And that's sort of one part of this GPU compiler abstraction as to how they sort of abstract a lot of things away. But as you kind of see right here, this program seems pretty simple, right? It takes some sort of index into an array. We'll get more into how it actually generates this index. And it basically just stores the value of AI plus BI and CI, right? And here we have sort of like the way in which you launch this kernel. And here we have assembly that sort of is meant to be like, okay, what does it look like on a CPU if we try to do the same exact algorithm? And this is mostly it, really. Pretty simple, right? But of course, this is a little bit more of a same example, but we sort of do a little bit more with this. We have in GPU programming, we have our data that lives on CPU. We will, typically speaking, before kernel launch, we will allocate memory on the GPU. And yeah, Nabil.
So is this page that we're looking at, is this like actual C++ code, or is that still the kernel page? Like doesn't look like C++, but what about this? Like,
this one actually, both of these are legitimate C++.
is it really? What's the triple thing?
Okay, so this is
well, it's only valid if it's compiled with NVCC or something like that, right?
Yeah. So like
so it's not standard C++, it's like got steroids.
Yeah, like so like a perfect example is that like so this is recognized by the CUDA compiler, but this is still quote unquote normal C++. Like if you try to go ahead and write to a file here, if you try to run hello world, if you try to make an API like a REST call or whatever, you could all do that within this body over here. Within here, you could do whatever you want. Here though, the kernel, you can't just make a REST call. You can't do whatever you want. You can't make a sys call and stuff like that. You're limited by what you can do because this is the actual code that runs on the GPU. This is just the invocation of that kernel. This is you essentially launching this function. But like, yeah, you can kind of see that this is none of this is really normal C++, but over here, you can do whatever you want. You could make a call to Google and, search something up or whatever it is you want. But here, though, you don't really have stuff like that. You're far more limited in what you can do. And, the bottom here kind of shows, okay, the kernel launch a little bit more fleshed out. In this case, we sort of have our data, which is sort of like, I guess, some random floats or whatever that we're going to be adding together. We create that on the CPU side. We allocate that, using CUDA malloc, right? So we copy those inputs over, and then we launch this kernel with some kind of like some launch parameters that we'll come back to later. We copy that back from the host, and we free up the memory on the GPU. This is all processed by the NVCC compiler, but this is still what you call normal code land. This is kernel land, where you're far more restricted by the actual code that can run. And getting more back into that, this is sort of what a kernel launch actually looks like. The kernel is sort of all of this, and this is 65,536. So by the way, I think we mentioned the word block before, and some people call it a thread block, but a thread block can contain a maximum of 1024 threads. And if we take this 65,536, we will see that we can go ahead and divide it by 1024, and we will get 64. So 64 blocks of data exist here. And in a way, you can go ahead and chunk this up into like, okay, each block IDX is sort of like, 1024 or whatever, right? So if this is like the 0th block, then you're dealing with the first 1024 elements, and then your thread IDX is your index within that block. Yes. Saad, do you have a question?
Yes, Professor. What happens if you schedule more blocks than are available on the device?
Well, see, I mentioned that a block runs on an SM, stream multiprocessor, and we'll get into what that is. But I mean, typically speaking, you have a queue, right? So it's not very often even, and most times, even on the highest end H100 and B200s, that a lot of kernels, most kernels don't fit on an entire GPU. Oftentimes, these thread blocks, they can be scheduled like independently though. So you can kind of like, if you have, let's just say 16 SMs or whatever, right? It will sort of like take 4 iterations, if you will, of these 64 blocks of, in one unit of time, you might have these first 16 blocks running on these 16 SMs, and they might be swapped out in sort of a queue fashion, if that makes any sense. But yeah,
But let's say you have 8 blocks available on some GPU, and you launch a kernel with 16 blocks. Will you ever see like one thread running where the block dimension is greater than 8?
That would be no. So you can no. Okay, so I use the word block and SM interchangeably, which isn't really the same thing. Block, you have a GPU with 8 SMs. A block runs on SM. So like you could have, even if you only have 8 SMs, you can have block IDXs into like, thousands, right? They can be 10,000 or whatever, right? That's not really like tied to the GPU. That's pretty agnostic of it. You just sort of have like, you have your kernel launch. That isn't really dependent on the device. You can have, 256 blocks or whatever, right? If it's on a GPU with 16 SMs or whatever, then they will run, and it will run through around 16 times, if you will, right? If you're dividing it up, versus a GPU with 32 SMs will run obviously a lot faster. But no, there's no like number that ties it to it. The code will still be the same, and you'll still have block IDXs up until like 256, if that makes any sense. Yeah, no, the software, the GPU runtime stack sort of manages all of that. So yeah.
Cool.
And kind of going into this is sort of like what you have here. You sort of have blocks, block 0, block 1. This is actually a two-dimensional block. So you kind of saw over there that this is like, 1 by n. This is a one-dimensional block. You can have two-dimensional blocks. Those are typically speaking, you typically have it depending on what data you're doing with. This could have been used for like see another hand coming up. Yeah, Nabil.
Yeah, is that a two-dimensional block or is that a two-dimensional grid?
Two-dimensional grid. Two-dimensional grid. Blocks are only like, really only ever like, that's, yeah, it's typically speaking, you can have launch
Why are the
grids
coordinates
of,
the blocks then?
sorry, what was that?
I was just asking. It seems like the blocks are like they have two pairs, coordinate pair, like an XY pair.
Yeah, you can have that within a block. But you don't typically speaking
So
have,
does that not imply that it's two-dimensional, or is that something else?
that's related to like kind of again like that's related to the fact that the grid itself is two-dimensional. So this is like 0, 0, this is 0, 1, this is 1, 1. This is within it's like a coordinate system, right?
Okay, so they're both two-dimensional.
Yeah.
Okay.
Okay, so so I've been using, and actually, you know what, I'll get back to this in a second. So let's first we were talking about like, okay, we have threads, right? Now, if you go back to here, and Nabil, I think you mentioned that like we have like vectorized instructions, right? But we never actually mentioned, okay, like look at this assembly right here, and look at this code, look at this kernel right here. Do we ever use a vector instruction? And I want you to think about that.
You just use a plus symbol.
There's a plus, right? But these are singular
It's just-
elements. This is scalar, this is scalar, and this is scalar. And the same thing happens in here, right? So here's a little bit of a kind of world breaker. That's not really how GPUs work. This is the kind of programming model of how you program it, but there is a little bit of like, okay, how does it actually run? And this is where we get into what we call a warp. We mentioned that earlier. Warp is technically something that the programmer doesn't 100% have to know about, but that's not really true when you get down to it. In reality, what actually happened within this this kernel, right? Which let's just say we had the length of 6,500 and 536, right? And let's just say that we launched it with 64 blocks and 1024 threads per block, right? Which is the maximum you can allocate. In reality, what the CUDA compiler did behind the scenes is that it went ahead and took these add instructions, right? And it turned them into 32 element vector instructions. So I think I actually have a slide all the way down. I'm kind of doing these out of order a little bit of, this is sort of like what you think this is like what the CUDA compiler is more or less doing, is that it's essentially taking your 30 your threads, if you will, it's taking them and it's compacting them into like 32 element long, let's just say vector registers, and it will add all of those together. So it gives you the illusion that you're running like kind of like you're running singular elements here, right? This looks like it's not a vector program, right? But in reality, it is. It's just the compiler hides that from you, if that makes any sense. Like in this,
sorry, I was going to ask, what's the difference between a warp and a block?
a warp and a block, right? So a warp is sort of like, okay, so I think I have a slide on that later, but a warp, since we kind of broke it, a warp is essentially just 32 instructions, right? 32 instructions that are like 32, a group of 32 threads that execute the same instruction simultaneously. And they must share the same program counter, and their thread indexes have to be consecutive, adjacent, and kind of like this. This is essentially, it's a warp of 16 for the slide perspective, but this is kind of like in our example where we're executing 64 blocks, right? A warp, what it might do is it might take thread index 0, thread index 1, 2, 3, 4, 5, from matrix A, right? And it might go ahead and load the same thing of B into this other vector register, right? Don't mind these ones right now. We'll worry about that later. And it will add them together. And that is kind of what a warp is. A warp is like, okay, a thread is kind of like how you program the GPU. A thread is under the hood. How does the GPU actually execute so much data at once? It's because it takes your threads and it coalesces them into warps. 30 sets of 32 of the same instruction, where you have the same program counter with data that's right next to each other, right? Contiguous, right? Contiguous data. So in reality, your warp is sort of just like, I guess once we get to the actual execution units, I'll show, it's sort of just a SIMD register, right? Even though you never used a SIMD register in your programming of it. Does that make any sense? Nabil, you there? Oh, right, okay. Yeah, but this is sort of stuff that's hidden from you by the CUDA compiler. And you mentioned blocks, and blocks are sort of like, so like, I guess a block will contain threads, and by extension, it contains warps, right? But a block is sort of like a partition of threads plus data, right? In this example, a block would sort of represent, in the 0 to 64 example, a block would represent threads 0 to 1024, right? And subsequently, it would represent the data elements of all these three arrays of 0 to 1024. That's what block index 0. That's what the 0th block would represent. And correspondingly, the block index 1 would represent 1024 to 2048, et cetera, et cetera, et cetera. And blocks do have one other characteristic that we'll get into later, but hopefully that makes a bit of sense, right? And in these kernel launches, we sort of divvy up how we access our data. So we sort of divvy up our data and our threads into these blocks, right? And as we'll see how the execution model runs, we'll see that later. So I kind of wanted to start off with kind of going into that a little bit further. I had this example of, kind of if you're trying to get a group of people from one place to another place, and let's just say we have 8 people in 2 cars, it might take 4 iterations to run those people between them. What the GPU does is that it somewhat gives you the illusion that you have 8 separate cars that can go to the same location, right? That can go to the stadium. But in reality, what the GPU is it's one large bus that takes 8 people at once. And that's perfect whenever you have to go ahead and execute a lot of multiplies or adds. But the second, maybe this person over here needs to go home for a second or whatever, the GPU programming model doesn't perform as nicely, right? That's sort of like, the bus has to go all the way here and then has to go over here. And if each one of these people, each one of these threads has to go somewhere else or whatever, you can kind of see how the GPU performance doesn't do as well. The GPU can functionally do all of this, but from a performance standpoint, you don't really get that great performance. So that is kind of something, a decent analogy of how GPU threads are actually handled. You think that you have 8 different cars, but in reality, you have one like bus. And the second you try to do anything that's like sequential, you are going to have a performance penalty in that sense. And kind of going more into this is, this is how in general a lot of GPU operations are handled using SIMD registers. We've already talked about warps and how they're, kind of what the qualifiers are for them, but let's talk about warp diversions, right? So GPUs, despite not being good at conditionals, still handle them decently well, or they handle them all right. And that is because of the fact that they can actually evaluate conditionals. However, as we mentioned, GPUs handle things in sets of 32, right? 32 elements, right? That's for a warp. And kind of here is a perfect example of what in GPU programming is called warp divergence, where essentially in this example, the bottom half of like the first half of this warp, right? The first, I know this is 16 elements, but just bear with me. Let's just say 32. The first half of these elements are, like masked, like, and the first half of this warp is handled here, and this else condition, the other half of the warp is handled. And obviously that's going to lead to a lot of serialization as far as like the actual GPU running it. But like keep in mind that this is still, and another thing to mention about this is that GPUs have something called predicate masks in front of their SIMD registers. And what that kind of allows is that like, if we want to do like you've kind of dealt with if statements in assembly, you'll have like maybe a number that's like 100. You might have a negative kind of like comparison number like 200. Let's say you have 200 elements and you made that negative or whatever, or 100, and you do like a subtraction instruction, right? These ones are going to represent data elements within that warp that are valid. So like you can make all of these 0 except these first two ones, and use that to go ahead and evaluate like a loop, right? In this case, there's other SIMD registers that can do modulo and division and comparisons, and this will sort of be used to evaluate a loop, like a for loop or an if statement and control flow. But you're certainly not making the best usage of your GPU. Does that make any sense of how like conditionals are handled? Any all good? Cool. So I kind of want to get a bit into the actual GPU architecture itself, and I'm also going to be covering a bit of something called Vortex GPU, which is like an open source Verilog GPU. It definitely, I'll be covering it and not going over specific like.
What's the difference between an accelerator and a GPU?
That's a good question, right? Good question. So like, take for example your TPU, right? I know TPU v5 or whatever can do if statements, but like a lot of these, you might have heard of the Sohu accelerator or whatever. It can't do any of this. You can't do any of like if statements, for loops, or whatever. GPUs are still what you call von Neumann compliant. They can still, there's nothing they can't do. They can do function calls. Dumb idea, but you can do that. You can do if statements, for loops, adding numbers, subtracting numbers, all that kind of stuff. Like an accelerator, like a TPU or whatever, it can really only do matrix multiplication, or like a Sohu can only really do like kind of like it has a transformer burned onto it, right? So it can only really do those operations. GPUs, they do have the ability to sort of run different algorithms and they can run sequential code. As a matter of fact, they're oftentimes used for sorting and other tasks that you associate a lot with CPUs. So like GPUs are able to be diverse in that perspective, and we could go more into like some specific stuff that GPUs have to accelerate AI workloads. But yeah, no, I mean like accelerators, kind of in a way, they're really just matrix multiplication devices, quote unquote. And if you wanted to, let's just say, train on a accelerator, there might be some difficulties because if you're trying to, a lot of optimizers live within GPU memory, right? And a lot of these optimizers, like Atom or whatever, require a lot of complex logic that the accelerators can't actually do, because accelerators can't do, like, they're not von Neumann compliant. They can't do if statements and for loops. It can only do a very, very specific set of stuff, which is why like a lot of these accelerators are mostly meant for inference. Does that make any sense?
Yeah, it does. Thank you.
All right, thank you. So speaking of AI, Ampere. This is like a kind of, you have a 30 series card or whatever. This is what I think we mentioned earlier. This is a streaming multiprocessor, SM. This is actually what runs a thread block. So we've got a few things to digest. We've got our instruction cache. In this case, this is for like, up there you saw kind of our instructions or whatever. I won't go into everything too much of detail. Warp scheduler, that's an important thing that kind of, schedules different warps. Like in this case, a warp scheduler would have a big deal in terms of like scheduling all of the loops within this. Kind of more or less a warp scheduler will sort of like schedule, it'll handle like, all of our functional units down here. And there's, so kind of like it'll handle conditional flow. It might like kind of do a bunch of latency hiding operations. Like if the warp scheduler executes a bunch of loads and stores or whatever, it might try to interleave that with some arithmetic to go ahead and hide the latency of the loads and stores. Warp scheduler more or less is kind of like kind of our, it's what executes stuff, it's what schedules stuff to be executed on the GPU itself, right? And kind of, by the way, I think I might have mentioned that the SM is actually not a single core. As you can see here, it's 4 of them, right? And there's a reason why, like I think earlier I mentioned what an SM is that it has some sort of shared memory, right? Now, this shared memory is actually accessible to the programmer. I think I have an example of that later. But shared memory is essentially a small but super fast kind of scratchpad memory. Global memory, which we haven't talked about too much, lives completely off chip. So it's kind of it's pretty long latency. Shared memory on the other hand, though, that's per cluster or per SM, and different cores within this, I think there are 4 cores within this SM, can, all write to shared memory. We're going to ignore these texture units. And yeah, so like zooming in on an actual physical core, we have our warp scheduler, which sort of will execute, will sort of like schedule. The basic scheduling loop is that it sort of schedules instructions that are, like we mentioned, the same instruction, executing on adjacent data, right? So it'll schedule warps that will execute adjacent data and adjacent threads as well, right? So like in our example, whenever we did the whole 64 blocks, one of our blocks would run on this entire thing, and they're sort of divvied up. Let's just say they're divvied up like 16 by 16 by 16 or whatever. So we have like 16 iterations that would happen here on this singular core here. The warp scheduler might go ahead and schedule like 0 to 32 loads, like, thread IDX is 0 to 32. It might execute, it might schedule a load to be done. And we also have a pretty large register file to handle all of these kind of like threads. But the one thing I also want to keep in mind is that it doesn't show it in this diagram, but we have like a scoreboard. Some of you might be familiar with what that is, but that sort of keeps track of, okay, which int32 or which one of these functional units is available. By the way, I haven't quite mentioned, these are more or less ALUs. This is an ALU, this is an ALU, this is an FPU, same difference, just for floating point. This is its own thing. We will worry about that later. I know it sounds cool, but we have load store units. This is kind of like what will interface with our shared memory, our global memory, stuff like that. Special function units, this will handle like cosine, sine, a lot of ML algorithms, a lot of graphics algorithms use a lot of trig. And this will kind of handle anything that's a little bit niche. But yeah, I mean, like conditionals, they can sometimes be done on like these ALUs, since, that's how a lot of, like, if you have a program assembly, you kind of know how, conditionals are evaluated. And then, yeah, I mean, we also have the loads and stores, by the way, are also connected to the register file for write back in case, like, whenever we update the value of a register. But we will go more into core specific details when we look at Vortex, because I think that gives a little bit more detail. Not a whole lot of detail in this, but does this kind of make sense? Yeah, so
Sorry, I didn't mean to raise my hand.
all right. I could continue to go into this, and by the way, I think that Saad, you were kind of talking about earlier, kind of like, okay, how do these kernel, or like what happens whenever we have like more blocks and SMs, and that's mostly just a kind of like a scheduling thing, right? We also have scheduling for like here we have blocks. Each one of these blocks gets their own SM, and they'll be swapped in and out. And also this diagram, this GPU, kind of shows you some other things like interfaces to DRAM. There's also like a DMA controller. There's a shared L2 cache for these SMs. Not to mention that, what else do we have in this? Yeah, no, that's like these sort of, yeah, these things will mostly just get scheduled onto these SMs. But yeah, you kind of see how, and this is the example I was talking about earlier, you kind of see how these are threads, but they're not really threads in the sense that they don't fully ever occupy a core, right? They sort of, whenever one core starts executing conditionals, the other thread pays the price. Where on a CPU, whenever as a thread you run, you can kind of do whatever you want, right? Going back to that example, that's something that I want to kind of drive home because it can be a difficult thing to understand with GPU programming. This is a bit of a complex example. I don't think we're going to get into this. This is sort of kind of like we talked about AI earlier. This is what kernels actually look like. And I think we also mentioned like, okay, like two-dimensional thread indexes and block indexes, and a lot of this stuff uses shared memory because global memory is a little bit slow. We'll maybe touch on that later. There's just some other slides at the end. Yeah, another thing is that like in GPUs, you rarely have the programming model exposed to you too much. Like you have PTX, which I might.
We can't see your screen.
Oh, right. Sorry. We have PTX or whatever, which is sort of like a virtual assembly, but we don't really have. I hope you guys like kind of understand that in GPU programming, a lot of this stuff is sort of abstracted away by the compiler, right? So yeah, I think I want to go ahead and show something else now, and that is sort of this diagram I made for Vortex. Vortex is an open source GPU developed by Torcha Tech, and this is sort of like Vortex has some of its own terminology, but this is kind of like an overview of like a small overview. Okay, you can configure these amounts, right? But here we have like multiple different cores, 4 of them, just like Ampere does. This is another thing that the diagram doesn't really mention, and that is that, all of this stuff is going to have like network on chip sort of limitations and, how they communicate, right? So there's going to be sometimes some contention with these network on chips. They all have access to shared memory in some capacity, so maybe it can draw some direct connections, but they can access shared memory. And if we want to step into like what like a full core looks like, this is sort of like what this looks like at a more granular level. Ignore this part. This is sort of like kind of what communicates with the network on chip. This is our warp scheduler, right? I have some Python pseudocode for like what that actually does, and it sort of like does what we were talking about earlier, right? It looks at different program counters. It looks at whenever it like kind of like it's what handles like branches or whatever, right? And it has sort of like, it keeps track of different warps within like the program. And sometimes like warps can be stalled. Sometimes they're active. It depends on what functional units are available, as well as if the CPU if a sync instruction is issued to the GPU, which that's a little bit more advanced concept. But yeah, this is sort of like in Vortex we have our instruction fetch phase. This is to fetch your instruction. This will decode it. Decoder is nothing too special. Sort of just which operands we're going to need, which functional units we're going to need, and we get to here. Our scoreboard is sort of. By the way, how many of you guys are familiar with like Tomasulo's algorithm and reorder buffers and all? Any of you guys? No, Nabil, I know you're familiar with it. We did this stuff together. Anyways, yeah, here's another kind of like interesting part of GPUs is that does anybody know like what the only true real like structural hazard is in a program like read after write, write after write, write after read? Happen to Saad? Yep or no?
I believe it is the read after write because
Read
you
up.
need to.
That's yeah, no, that's right. So the way we mitigate that in a GPU is for the most part, I guess scoreboards, unlike an ROB, scoreboards don't actually deal with read after writes. In order to deal with that in a GPU, we just don't allow two threads to have the same instruction in flight within the pipeline. Like your typical Intel CPU is going to have like 17 stage pipelines. This has 5. And that's pretty indicative of any other GPU. By the way, like, yeah, you don't really have stuff like speculative execution, long pipelines, branch prediction. None of that's really happening in a GPU. Maybe some branch prediction might happen in the warp scheduler, but if it is, it's kept a secret. So yeah, Nabil?
Could you explain how we don't have like read after write dependencies, or how it's not allowed?
Or okay, so basically we have like multiple like for each thread, right? For each thread, like read after write hazards are usually kind of like they're usually considered like pipeline hazards, right? Within the pipeline, if we have like if we have an instruction within the pipeline that is going to modify data that another stage in the pipeline that it'll read or whatever, right? We just don't allow like the warp scheduler will never allow multiple threads to be active like in the same like in flight in the pipeline at the same time, right? So if like thread
So,
I
isn't that what scoreboarding is?
kind of that's kind of scoreboarding is more or less
Look at which registers are, I guess, yeah, which registers are in use, and then just don't allow instructions that are dependent on those registers to go into the pipeline.
yeah, so scoreboard will kind of look at which registers for which threads, but it'll also look at which functional units. I think that like I kind of just put singular ones of these, but in reality, these GPUs, like you saw, Ampere has hundreds of functional units. So yeah, no, the scoreboard doesn't quite deal with that all of itself. The warp scheduler is also responsible for, like you saw earlier, like here we have like active warps and stalled warps. If we have some sort of read after write dependency, the GPU might just go ahead and just like put like that warp that would cause that issue into like the stalled category, until write back would go ahead and like clear that up, right? So
that's pretty similar to how CPUs work. It's just on the level of warps instead of single instructions. Yeah.
that's true, but like I think another thing to mention is just that like CPUs in general, like they have like like 15, 16 stage pipelines. GPUs like are really only gonna have a max of 5. Even like the most sophisticated GPUs. Like I think I'm trying to drive the point home that GPUs just don't have a lot of the kind of sequential logic advantages of CPUs. CPUs have branch predictors and all sorts of other long pipelines to deal with. GPUs just don't have that, right? They just again this stalling of warps. If you try to do that in a CPU, you definitely would be getting completely optimal performance. So yeah. By the way, so kind of like here are some of the functional units that the scoreboard actually handles. This one I've yet to fill out, but this is an ALU. This is like a floating point unit. You use it for adding to, like, you have FMAs, which if you've ever in ML, a lot of ML will use FMA for matmals. We have tensor cores. I haven't filled that one out yet, but tensor cores. By the way, can anyone tell me like what a tensor core, like another name for a tensor core? I think you guys might know.
Matrix multiplier.
I was looking for a systolic array, but I mean that works as well. Yeah. Yeah. So by the way, tensor cores are a bit of a oddball thing. I guess also the SFU is as well, where tensor cores will only ever the programmer has to explicitly use tensor cores. Kind of, like we saw earlier, the GPU compiler will sort of just like take those scalar instructions and sort of put them into warps and stuff like that. Tensor cores are kind of their whole different animal, which is why we don't really go into them too much today. But yeah, then we have our load store unit. This will sort of handle our access to main memory. It'll handle our access to shared memory. Shared memory, by the way, is like, I guess, like, not going too much into it, but global memory is considered significantly slower than shared memory, right? Because one's off chip, one's on chip. And if you're looking at ML, a lot of like ML algorithms like flash attention kind of get their speed from sort of loading everything to shared memory, working on them, and then sort of like then just storing back to global memory. So this is kind of like your basic architecture of a GPU core. And yeah, I mean, this is sort of like, this is a cluster, I guess. Vortex calls it a cluster. It's called an SM in NVIDIA speak. By the way, and AMD has their own thing called like a wavefront. It's 64 elements, but it's the same just as a warp. But yeah, they're all sort of the same thing, right? Does this kind of like clear up some of the I guess kind of like, okay, this is how you program a GPU. If we really want to, I guess kind of this is the last thing that I might touch on, and that is that if anybody wants to try to make sense of this matrix multiplication kernel, if anybody's feeling down for it.
I'm not gonna lie, I do have to leave pretty soon for the
Okay, yeah. Perhaps next session, I think that like I don't want to cover too much AI stuff. I think next session I might go more into warp divergence and actually like what's it called? And like some more AI stuff like matmals, tensor cores, all of that jazz. But yeah, I mean, I think that we can call it a session here. Hopefully you guys all learned something in this. And yeah, any questions? Any last questions? Thank you, Saad. All right. If that is all good, then I think we can end. Oh wait, Saad, do you have something to say?
No.
No, you
Not
good?
yet.
Okay. Yeah, I think we can call it early. All right. Thank you everyone for attending. Hopefully you learned something. Oh, okay. Just gonna put that. All right. Well, thank you guys, and I hope you have a fantastic.
All right. Assalamu alaikum.